Hey guys, Oric here. Just a quick little video on some notes for, I call it Unit 10, but on exponents and logs. And I'll do a couple of examples and put this on our Google Classroom so you can check it out before we do the practice test video. So exponents and logs, why we do logs is to solve for exponents. And we started this with exponential growth and decay, and I mentioned some problems like, you have a penny and you double it every day for a month and you end up with over $1,000,000. And exponential growth is when you have the x, if you will, is in the exponent. So an equation like this, y equals 2 to the x power, would, when x is 1, it's 2, then 4, then 8, then 16, 32, 64, and it grows really fast. The penny example would be this equation. 0.01 would be our initial amount, and then we double it for, let's say, 30 days. And just for fun, let's just see what that is. 0.01 is what we start with, times 2 to the 30th power. And let's see, $10 million. So yeah, it's a pretty good chunk of money. So that's our general equation, and we might recognize this from our geometric sequences. This was our starting amount. This was our R, so we were multiplying by 2 every time, and then of course we used n when we were doing series and sequences. Now we're usually the exponent's going to be time, and the general formula for like compound or for interest on an investment is your amount that you're going to have is your starting amount. So your A1 in our one example, that's going to be our, we call it principal or starting amount, and then 1 plus whatever rate. So 100% is 1, and so 1 plus 1 would be 2, and that would be this equation over here. And then to a certain amount of time, in years usually. And so recall that most interest rates are going to be like 5%, 6%. So just as a quick example, if I have $1,000 and I want to find out how much money I'm going to have at 7% interest, I go 1 plus 0.07 to, let's say, 8 years. And that will give us our amount we'll have after 8 years. So initial amount, our rate, and our time. And 1,000, 1.07, that's 1.0 plus 0.07 to the 8 years, and we have $1,700.18. That's compound interest, but compounded annually. That's our general formula. Depreciation, it would be an amount would equal our starting amount. I'll do a different color. Let's go green. Our starting amount, like a car, for instance, 1 minus the rate it's depreciating at, time. And so let's say we have a $10,000 car, and it's depreciating at a rate of 15% per year. So 15% is 0.15. And how much will the car be worth after 5 years? So $10,000, this is 0.85, and this is actually called the decay rate. On this one, 1.07 is the growth rate, and then for 5 years. So how much is our $10,000 car worth? 0.85 to the fifth power. We're less than half, $4,437. $4,437 after 5 years. That's probably fairly accurate. Maybe they depreciate a little bit more, a little less. Compound continuously, and I'm not going to get into that in this video on how we come up with this number E, but the number E on the calculator is right above the division sign. And if I just put in E, it's a number that's a little less than 3, 2.718. And it comes from a compound interest formula. So when we compound interest, we take this interest rate and we divide it by how often we compound it. So the general formula is our amount, let's go a different color. Our amount equals our beginning amount 1 plus the rate over n, and for a certain amount of time. So for the example, I'm going to use quarterly. So every 3 months it's going to be compounded. So if we have $1,000 compounded at let's say 5% interest, or let's go 5.5% interest, so you can see what that looks like. 5.5% interest would be 0.055. Think of the whole number 5%, and that's 0.05. You move the decimal point over 2 if you want to see the percent. And quarterly would be 4, monthly would be 12. And then for compound interest, I should have put that up there, that's T times N. So let's do it for 8 years, and we have to multiply this by 8. And on your calculator, you want to just raise this to the 32nd power, especially with the older calculators where you can't put it in the otherwise you have to make sure you put this in parentheses in your exponent. When you put this, and then the exponent is this symbol, and then go 8 times 4, but better just to put 32 so you don't have to worry about that. But if you raise it to an exponent and you go whatever this number is, whatever's in parentheses, to the 8th power, and then you times by 4, it's going to raise it to the 8th power and then multiply that whole thing by 4, not raise it to the 8 times 4 power. So here is what we would have. We go 1,000. Well, let's do this. 1 plus 0.055 divided by 4. Enter. There's our number that's in parentheses, and I'm going to raise that to the 32nd power. Now 1.548, that's what I'm going to multiply by 1,000. So I'm going to times 1,000. 1,548, I'll just put it as that. $1,548. And let me go a different color. That same formula for compound, what's called compound continuously, is P, that number E, to the rate times the time. So if I do the same numbers, $1,000 compounded continuously, like every second, 5.5% is 0.055. Make sure you don't put 5.5 because that will give you a huge number. 0.055 times the rate times the time, and we did 8 years here. And so on the calculator, e to that power is just, e is just a number. So if I go second, e to the 0.055. Once again, my calculator is the newer version, so I can actually multiply up there in the exponent. Otherwise, you'd want to multiply that ahead of time or put it in parentheses. Times 8, enter, and then I'd multiply that by 1,000. It's not going to be too much different. 1,553. $1,553. So you can see we made $5 more compounded continuously versus compounded quarterly. Okay, that's all of the interest and growth problems. I'm not going to do a half-life problem just to sake of keeping this a little bit shorter. Now, so the main couple of formulas you want to remember for logs, and logs, which we're going to solve for t. So to kind of stick with the same example, if I have $1,000 and I have 5.5% interest, I'm going to scroll it up here. I'm going to say $1,000 at 5.5% interest, and I'll just use our first formula, 1 plus 0.055. And I'm going to say, how long is it until we have $2,000? So we need to solve for t. That's the whole point of using logs. So I divide both sides by 1,000. That's going to give me 2 over here equals 1.055 t. Now here is the general form of that you kind of want to remember, or at least you know where to find it in your notes. A to the b power equals c is the same thing written as a log, as log base a of c equals b. So now c becomes the number we're taking a log of, and b, our exponent, is what it equals. So we can solve for t. So if you look at this problem right here, c is 2. This is my c. 1.055 is my a, because it's a to the b, and so t is my b. That's not multiplying, that's just b. So a to the b equals c. So if I want to write that as a log, I go log of base. This is log base, so it's down here in the, it's not multiplying. Log base 1.055 of 2, log of 2 equals t. And now I solve for how long that's going to be to double. Go from 1,000 to 2,000. And then one other formula. So here's one formula that you really want to use, and the other formula is log base a of b. Now when you look at your calculator and you see log right here, and I take log of 100, that is 2 because it's log base 10. They don't show the log base, but it's always 10. So 10 to the second power equals 100. So log base a of b, if it's not in base 10, this is the same thing as log of b over log of a. And actually, of any base. I can use natural log, I can use log base 3, but there's no log base 3 either. Log of a. So log base, so if I go, so this problem here, now scrolling back down, so to use this formula, let's undo that. Go black. Here's our two formulas that we want to use. I'll circle. So if I go back to red and I want to solve using this, this is the same thing as log of 2 over the log of 1.055. And that equals, I'll pull my calculator out, log of 2, close off the parenthesis, divided by log of 1.055. Enter 12.95 years. 12.95 years for my 1,000 to turn into 2,000. And if I want to check it out, I'm going to put this in the calculator right now. So I have $1,000, 1 plus 0.055, kind of simple interest, compounded annually. It's really compound interest, but it's compounded annually. And now I just see my videos here is a little close out, but that's a T right there. That's got a little bit cut off from my custom view. And I said 12.95 years. Now that's rounded off. I'm going to just put second answer here because my answer was 12.946. But if I put 12.95, that would be pretty close. But I can just check and make sure that works. $2,000. So I put that in at 12.95 years, and I have $2,000. All right, so that's how you use logs. It's to solve for exponents. Here's the main two formulas. I'll just call this formula number 1 and this formula number 2. That's the real gist of this whole chapter. If you can use logs when you have a problem where you need to solve for an exponent, and then you can use these different compound, simple interest, compound, here's like a simple interest, here's compound interest, which I think is the hardest one, and be really careful on this one on the calculator. And then this is your compound continuously. I'll actually even circle that on here too, and I'll put these quick notes up on our Google Classroom as well. Right there and right there. This is compound continuously, compound interest, where n is how often you're compounding, and our simple interest and decay when you have like a car depreciating. All right. Thanks. Have a good one. Bye.